This is a short training video on the Night Time Microphysics RGB. I'm Scott Lindstrom from Sims. This RGB has a long history, starting in UMetSat, building off the works of Lenski and Rosenfeld, and that continues today. Its use has accelerated in the United States since the launch of the GOES-R series of satellites. Use of the RGB will allow a forecaster to interpret a variety of things. For example, one can differentiate between high and low clouds. You can also differentiate easily between cloud type and cloud phase, and the RGB can identify a variety of thermal anomalies. This table shows the Night Time Microphysics RGB recipe, accompanied by the animation of GOES-16 imagery over the CONUS sector on December 16, 2019. One useful aspect of this RGB is the ability to easily identify cold cirrus cloud features, darker shades of red to purple, mid-level mixed-phase clouds in shades of orange, and supercooled stratus clouds, which are pale cyan in warm regimes, and brighter shades of yellow in cold regimes. Here is a closer look using GOES-17 data to show a variety of cloud types across the northwest United States on December 2, 2019. Shallow areas of fog, shades of gray to pale cyan, are over parts of far western Washington and Oregon. Farther inland, thicker fog and stratus, which are lighter shades of yellow, covered a broader portion of those two states. Patches of thicker mid-level mixed-phase clouds in shades of orange were moving across northern Washington and from Idaho into western Montana. The fast northeastward flow of a mixture of high-level and high-altitude cirrus cloud types, shades of orange to red, was associated with a subtropical jet moving into Montana, and toward the end of the animation, an isolated patch of orographic cirrus with darker shades of purple developed over western Montana as the strong winds interacted with the rugged terrain of the northern Rocky Mountains. The RGB can effectively characterize all of these different cloud types. In this example, a broad supercooled stratus layer covered much of the lower Ohio River Valley on December 3, 2019. However, embedded within the stratus were several narrow industrial plumes, likely from coal-fired power plants, that appeared as brighter shades of yellow. Emissions from the power plant cooling towers contained particles that acted as cloud condensation nuclei, which effectively seeded the existing stratus cloud layer, and this initiated the formation of smaller supercooled water droplets. The presence of these smaller cloud droplets changed the green component of the RGB combination, the night fog brightness temperature difference, 10.4 minus 3.9 micrometers, resulting in a brighter yellow appearance to the industrial plumes. Note also the cirrus clouds with embedded condensation trails moving in from the west at the end of the animation. Condensation trails or contrails are apparent in the RGB because the split window difference, which is the red component of the RGB, effectively detects contrails. This animation shows an example of a relatively thin and shallow advection fog moving northwestward across South Texas and the Rio Grande Valley on November 19, 2019. The dull gray to pale cyan shades are typical of optically thin features in warm temperature regimes. Near the upper center portion of the images, clusters of darker pink and violet pixels represent hot thermal anomaly signatures of natural gas flaring from fracking activities in the Eagle Ford oil shale formation. In addition, dark purple filaments of cirrus clouds are moving eastward across the region, especially at the end of the animation. In this example, a narrow rope cloud defining the leading edge of a cold front is apparent moving southward along the Gulf Coast of Mexico. With surface analyses only available every 3 hours, the exact location of the cold front could be determined and tracked using the Nighttime Microphysics RGB, and this can be helpful in determining the timing of an abrupt wind shift in an area having sparse surface observations. Here we have an example of stratus clouds in a cold regime. The stratus will exhibit brighter shades of yellow in the nighttime microphysics RGB imagery in cold air than in warm air, where the clouds are more of a cyan. This is because of the reduced contribution from the blue component, which is the 10.35 micrometer. So less blue changes the cyan to yellow. Of note on this day was a lake effect cloud plume streaming southeastward from still unfrozen Fort Peck Lake in northeastern Montana. As this cloud plume eventually moved over Glendive, light snow was reported at 12 UTC. This shows another example of stratus clouds in a cold regime, here over interior Alaska and the Yukon. When strong radiational cooling occurs over a snow-covered terrain, the arrival of a stratus deck can often have a marked influence on surface temperature trends. This was very evident at Bettles, PABT, and Fort Yukon, PFYU in Alaska, with warming occurring as radiational cooling was slowed or even reversed while the stratus moved overhead. Temperatures continued to rise at Bettles as the stratus cloud coverage remained broken to overcast, while the temperature briefly dropped again at Fort Yukon as the cloud coverage thinned to scattered. The nighttime microphysics can also show convective outflow. In this case, severe thunderstorms had been moving northeastward across the high plains on May 27, 2018, producing tornadoes and large hail in Colorado, Kansas, and Nebraska during the afternoon hours. After sunset, the nighttime microphysics RGB efficiently revealed the thunderstorm outflow of low-level stratus as it spread southward across northeastern Colorado. Note the speckled appearance of the cold thunderstorm tops. This results from the use of the 3.9 micrometer shortwave infrared data in the green component of the RGB product, that is in the night fog brightness temperature difference. 3.9 micrometer has low precision at very cold temperatures. As a result of that poor precision in the 3.9 micrometers relative to the 10.3, you'll see speckling in the RGB over very deep cold clouds. On May 25, 2018, severe thunderstorms produced a nearly continuous path of large hail, as large as 4¼ inches in diameter across North Texas. After sunset, the nighttime microphysics RGB showed the northeast to southwest oriented hail swath. This is because the 3.9 micrometer is more sensitive to low-level temperatures. It detected the cooler temperatures there when the 10.3 did not, so the green component of the RGB, the night fog brightness temperature difference, the 10.3 minus 3.9, had a larger signal over the hail swath. Here's an animation of the nighttime microphysics RGB, and the hail swath was apparent in a gap between two southward moving convective clusters. Low-level outflow boundaries produced by each of the two thunderstorms are also apparent. This slide summarized the important aspects of the nighttime microphysics RGB. Additional information and examples can be found at these resources. This concludes this short training module. Thanks for listening.